Hey, well, there aren't very many people here, but we'll get going anyway. So we don't have too much left. In fact, we may be able to get through just about all of this today, which gives us some options for kind of where we go from here. But we're starting development of our second game. I'll check in with people on Friday with regards to what your design is, what your implementation goal is, how you're planning to best what you produced for the first game, although that's going to be a bit of a challenge given how good I think everyone's first games were. So we'll see. Anyone have questions before we dive into the actual used temporal difference learning algorithms? All right. I will summarize that and we'll get the ball rolling, no pun intended. This is not a marble roller. All right, so we were talking about different temporal differences, kind of what temporal difference was, and then the fact that on policy and off policy was still an important consideration here. We ended talking about SARSA, the on policy temporal difference learning algorithm. And as usual, with whenever there's math on the screen, there is a lot less complexity to that than it would otherwise look like. Let's talk about this temporal difference error as to what all of these represent, because it's been a little bit since we talked about this. But now we're getting more and more familiar with reading this, so maybe I can get some assistance with this. Can anyone interpret what's going on here for this temporal difference update? So remember that an update is just when you take an existing value and you update it to consider additional experience. So we're in some run of this and we reach a new state and we want to update the state where we came from based on that information. Actually, it's really state action pairs, but we want to update the value of that state action with the new experience that we get. So what's happening? What do these things represent?
The P plus one, the new experience.
T plus one is the new state. So if we're going from a state to a state via some action, time t is the one we came from, time t plus one is the one we're arriving at. Let's just kind of start at the beginning. What is Q?
Value.
Yeah, it's the state action value. So the new state action value at time t is going to be the old state action value at time t plus what's alpha? It's our learning rate. Yeah, it's how much we are weighting the new sample that we are getting as we're making this run. So as alpha gets closer and closer to one, we're biasing this as this new piece of data that we're collecting is more and more important. In the extreme, if this is one, we're going to throw away what this used to be. And we're going to say that whatever we just experienced is the entire history. And if alpha is zero, then zero times anything is zero. We're throwing away this example. So usually this is 0.05 or 0.1 or 0.01. We want somewhere between 1% and 10% of our overall history to be based on this new data point that we get. So we're going to multiply the value of the experience that we get, which is this TD error, by the learning rate so that it doesn't overwhelm the old value. We're going to be making a small change to the old value based on the new value that we get, because this represents a larger sample size, and this is a sample size of 1. So we're going to update the old value by some small percentage of the new data point. What is R? It's the reward as we get to that state. So if there's a movement-based penalty, like we talked about the maze where the movement penalty is always -1, this would be for moving from state action pair at time t to the state action pair at time t plus 1, when we get to that new state action, we're going to have received a reward from the environment based on the action that we took. That is that reward. This is not the reward for ending the game or anything at the end of an episode. This is just the reward for the movement between the old state and the new state. What's gamma? Yeah, the discount factor. Yeah, or discount rate, either one of those would be fine. But it's a decaying factor between if we're looking or analyzing far into the future, how much are we discounting rewards in the future? Because the state action pair that we see at time t plus 1, we don't want to immediately say that, I don't know, this is one time step in the future. So if we get the same reward here versus here, what is the proportion of how useful or relevant the new one is compared to the old one? As the new one is farther in the future, we discount it by some amount, and we leave that as a variable because different problems are going to have different relevant discount rates. This could represent inflation. If you're being paid today versus paid next month, the money will be less valuable in 1 month than it is today, unless it accounts for inflation. All right. We also have a state action value for the state and action that we're arriving at. And this just represents this entire quantity is the difference between the one that we arrived at and the one that we got to. So this is just saying the new value, we improved our state action pair value, hopefully, when we make this move. But that's either going to be positive if we've improved our state. It's going to be negative if we're in a worse state than we were in before. But this value subtracted gives us kind of the change in how valuable is where we are compared to where we were. Discounted, add the movement penalty or other reward that we get for that one action, multiply it by the learning rate. And that's the change to the existing value of the state that we came from, because we get one more example of going from that state and receiving a reward and being in a position that is either better or worse. Yeah.
The Q on the right side of the arrow, that's from the previous one that we're coming from.
This one?
Yeah.
Yeah, this is just an update. This is like saying, if you're writing Java code, x equals x plus 4. The new value of x is the old value of x plus 4. The new value of a state action pair is the old value of the state action pair plus something. It's a way of modifying. It's just an assignment statement.
So each time we're just iterating by the TDR.
Yeah, we're learning based on this single example. This is what we thought the value of the state was. And now we have one more data point of something that differs from this by this TD error amount. So we're going to learn and either bump this up if we're in a state action pair that is better than where we came from, or bump it down if we're in a state action pair that is worse than where we came from. Kind of in the driving home example where we had the arrow that was telling us pushing up or down toward what we experienced. This is what we experienced. This is our baseline of what we think. So we're going to update it based on the difference between what we experienced and what we thought we were going to experience. This is what happened. This is what we thought was going to happen. That difference is incorporated into what we think is going to happen in some capacity. So this idea, we can do exactly the same thing that we've done before, changing our policy greedily. We can do that. And if we implement this in pseudocode, we see that really all that we're doing is for each episode, we initialize our initial state. And we choose an action from that state using the policy. So we just use the on policy action selector. And that chooses the action. And by the time we hit this inner loop, we've now selected a state action pair, which is what's necessary. Remember that the left-hand side of this is QSA. It just means that we have a value for a state action pair. So we initialize the starting state and we pick an action from that starting state according to that same policy. Now we have that state action pair, we have a queue. For each episode, we're going to take the action that we chose, observing the reward, finding ourselves in the new state, then choosing the new action from there. And that gives us the new state action compared to the old state action. This is Q time t plus one. This is Q time t. So t plus one. And then once we have the t and the t plus one, we can just plug and play the experiment from the last slide. We're going to calculate our TD error. We're going to use that to update the old value of the Q for here based on what we just experienced. Then we update the value of our state, update the value of our action to be the new state and the new action, and we loop around and pick the next state and the next action. We observe the next state and pick the next action. That allows us to loop until the episode ends. And this allows us to learn online based on the differences of what we expect and what we witness. Every state is going to be updated every time it's visited, which is nice. I will give you an example. Because we like so many grid worlds, and here we're going to make another grid world, but this is windy grid world. This is the amount that when you enter this column, you are bumped upwards. So wind is flowing from south to north. Here you enter this. Sorry, I think it's going to leave. If you leave this, you're pushed one cell up. You leave this, you're pushed one cell up, etc. The goal is on the other side of the wind. In fact, it's in the wind on the other side of the wind. And so in order for this to even be successful the first time, we have to, you can't approach the goal from the left. It will push you up above the goal by the time you get there if you try to approach from the left. So you have to approach from the right in order to reach the goal. So same thing, actions are our four directions. The reward on each time step, the R and the TD error is going to be -1. So every action is -1. That tells us that a run that finds the goal faster is better. So for all policies, there's no guarantee for termination. You could just fiddle around forever and never find the exact path. You two have to happen upon it. But the idea at that point is we would start to see the values of areas around this changing. And then as we continue to explore the space, what we learn as we get close to the goal will start to expand outwards, even within the same episode. We don't have to wait for an episode to terminate in order to start doing those updates. So it allows online learning during an episode without waiting for that episode to terminate. What do we want to guess? So we're going to start with a fairly random policy. And the idea is that when we terminate an episode, we're going to update that policy and try to learn from what transpired. But then we're also going to use SARSA as we explore this space to propagate. How many moves do you think it takes to solve this game for the first time?
Randomly?
Yeah, using a random initial. So we start in the start state. There's a 25% chance of going left, up, down, or right. And the goal is eventually reach this goal. How many steps will it take to solve the game for the first time?
304.
300 and something. I like it. It's a good guess. Anyone want to say they think it's higher or lower? Yeah?
I could theoretically move backwards then too,
Yes.
if you've already,
It can do the entire exploration of the space. The wind kicks in if you move out of one of the cells that are windy. It pushes you as you move. Obviously, you can't get pushed out of the beyond the north border. You get stuck on that. Any other guesses? So we're gonna look at how many episodes, and each episode is finding the goal. We're gonna look at the total time steps on the x-axis and the episodes on the y-axis. So the steeper the graph, the faster it's solving it. The flatter the line, the slower it's solving it. Here's what the learning looks like. It looks like it solves it for the first time, right about, is that line flat to there? I think it actually might be 2,000-ish steps to solve it for the first time. Once it solves it for the first time, it's actually able to reasonably figure out how to take less time. But you can see that it's completely learned really by this point. There's not a ton of learning to do as we go from that slope to that slope. It kind of is, it's fairly flat at that point. It's stopped learning. But it figures out that it only takes 50 to 100-ish time steps, however long the last slide was. How many steps is that? That's really only 20-ish steps. Something that's optimally learned should only be taking 20 time steps to solve a single episode. But you can see what kind of slow learning looks like as it has to randomly find its way to the goal. And if the goal is so far removed from the start state, that initial learning is incredibly slow. It can't do anything intelligent until it's randomly won the game or randomly done something with a positive value. Once it does that, then in future episodes, it doesn't need to solve the game to continue learning from the experience in the last game. It will start to propagate that information outwards as it explores, gets close to the goal and then farther away from the goal. As it gets closer, it's going to start back propagating that information one step in the direction that it came from. And that allows for the temporal difference to really be an online learning type of algorithm. Any questions on Windy Grid World or how this works? If you have the exploration built into the policy, you just kind of have to do this. You're going to wait until the episode ends randomly. And Windy Grid World is not even that big of a state space. Like, this is not a big state space. There's just a constraint on this, and now it takes a very long time to find the goal for the first time. So if you're going to build any kind of learning into an AI agent for a game or something of the sort, think about how complex it is for it to start receiving data. Because targeting this very early part of learning, this is where transfer learning works really well. If you can either have a human come demonstrate, like, imagine that you are responsible. All you need to do is play and beat Windy Grid World. If I gave you this problem on an exam, no coding, no reinforcement learning, and I just say, what are the sequence of steps that are needed to reach the goal? You could pretty reasonably quickly come up with a good path. It doesn't even have to be the optimal path. If you could demonstrate that path, and then instead of waiting for a random process to find the goal, we say your first experience was this human demonstrated experience, now go. All of this work was done in 8,000 time steps. We can shave a quarter of that off by demonstrating a reasonable solution before starting training. Okay, let's talk off policy. So Q-learning is our off policy temporal difference learning algorithm, and it looks a little bit different. What's different between Q-learning's error and Sarson's? Where is this different? Yeah.
Taking maximum actions on state.
Yeah, so it's right here. What was that with Sarsa? This was. That's what that was with Sarsa, the action at time t+1. Now, instead of waiting for an exploratory action to pick the action, we're going to do the analysis. We're going to figure out which action was best here. And remember that we're using two policies. We're using an exploration-based policy, and we're using a target policy that we're actually learning. The update is to the target policy because we don't learn the behavior policy. So we are changing how good we think states are without changing what we do. So there is no action selection in this. We're going to analyze what was the best one to pick, and we're going to use that when we feed the information back. So we have a prior state at time t, we have a new state at time t+1, and there's going to be an optimal state out here at that as well. So our behavior algorithm is going to go say, instead of continuing to sit here and listen to this boring lecture, I'm going to go jump out the window. And we shouldn't learn from that. If we were using Sarsa, we would say, well, what is the value of being in this state while you're sprawled out on the concrete below, wondering how expensive this is going to be if you're still thinking. When you backpropagate that, that's going to make this look bad, but this was an exploratory action. It would be ideal if we could use and say, when we update the value of this state, since this was bad, let's update it as if we'd done the better thing. As if we continued to sit and listen to the boring lecture. So what we do and what we learn are different things. So this maximum is saying, instead of doing what we did, we're going to look at everything we could have done, and we're going to pick the best thing that we could have done. The action that we take might change our mind on what we think the best thing to do is. If it does, then we use that data to backtrack. But if it doesn't change that, then we're going to use what we should have done instead when we analyze what we should have done. It's very much like thinking back over a bad decision that you made in your life, replaying it over and over in your head, over and over and over again. And then eventually you think of, what if I'd done that instead of what I actually did? You could learn how to act in the future, not based off of the action that you took, but the action that you should have taken. And that's what we're trying to emulate with the off-policy Q learning. We're saying, if everything that I could have done, let's go analyze and learn based off of the best thing that I could have done. Just because I went on a date and I insulted the person's clothing, I shouldn't learn that that is a bad, yes, I'm going to take into consideration that that was a bad thing, but I'm going to learn from this like as if I didn't do that. So that's the big difference when analyzing language. And if we look at Q learning pseudocode, we see that it's basically exactly the same as Sarsa's, with the exception of we choose the action using the policy that is our control policy and not that is our learning policy. When we take the action, when we update, we're again doing it on the maximum. So we're not updating this. There's no capital A anywhere here. The only capital A is what we expected. Instead of this is what we did and this is what we expected, this is the best thing we could have done and this is what we expected. This is only going to change now if our view changes and or if we've converged. Yeah.
If it always updates based on best action, we could have taken as ever lower the value of the state, since it's always updated on the best one.
See if I can get that. Say that one more time.
Since it always learns best action.
Yeah.
Lower the value of the state that it's biased.
Yeah, if we take the action that we think is best and we find that that's not as good as we thought it was. In all one time that I've played the lottery, I've won the lottery. That seems like the best action to take. Eventually, I would learn through repeatedly doing that, it would start to approach the actual expected value. And once that expected value dipped below the price of the ticket, then I would stop buying lottery tickets and say the best action here is to not buy lottery tickets? That is a great question, though. So, but once it's converged to that actual expected value of the lottery, then you'd have to have a small sample deviation from that to swing back into doing that again. But just because the expected value is dipped below the price of a ticket doesn't mean that you should stop playing because you don't know what the actual expected value is. You just know that your experience so far has said that the expected value is negative. So you will still continue to explore to gather that data, but maybe less frequently, because now the optimal thing to do, it's an exploratory action to play, not an exploratory action to not play. Does that make sense to others as well? Other questions I can answer here? Let's illustrate with another example. We're going to compare SARSA and Q-learning with the cliff walking example. So this is another grid world where the bottom row of the grid world minus the start and the goal is called the cliff. If you enter the cliff for any reason, you immediately get a score of -100 and the episode restarts. The goal is to get to the goal as fast as possible. One of these arrows is drawn with what SARSA converges to, and one of them is drawn by what Q-learning converges to. Anyone want to take a guess as to which arrow is which algorithm? Yeah?
I think the safer path is SARSA.
Why? You are right.
Buildings, but I think they've been going on for all the time.
Yeah, since what it's doing and how it's evaluating what it's doing is based on what it did, then it's going to learn to avoid the cliff. Because you can imagine that you're not in control of your own actions. You can think, don't fall off the cliff, and your body just doesn't listen to you and falls off the cliff. If that's the case, then the path that you're going to take, because you can't trust your body, is to get away from the cliff so that when your body doesn't do what you thought and moves a step closer to the cliff, you're not off the cliff yet. And you can correct for that. And since your body usually listens to you, you can start to move away from the cliff and you're not going to fall off the cliff as much. Why does Q-learning hug the cliff? Yeah.
It just takes a step into cliff and says, oh, I shouldn't have done that. Keep doing
Yeah, it falls off the cliff. And then when it analyzes why did I fall off the cliff, it thinks, well, I should have moved forward anyway. That was an exploratory action. I'm going to throw away that happened and pretend like I moved forward instead of fell off the cliff. And it recognizes that the best way to get to the goal is to hug the cliff, even though while it is learning, it's falling off the cliff all the time. So as these two algorithms are learning, which one's performing better? SARSA? It is SARSA. Because Q-learning is going to be following its behavior policy, which is going to be close to random, or it's going to have exploration built into it. When it makes exploratory actions, as it's hugging the cliff, it's probably falling off the cliff at some point. It has to make this right decision, this right decision, this right decision, all sequentially in order to get to the goal. If it ever decides to go down, if any one of these is an exploratory action, you're off the cliff. So Q-learning will not perform as well as SARSA as it is learning. Once it has learned, and Q-learning switches into using the optimal policy that it's learned rather than its target policy, which algorithm performs better? Q-learning. So that tells us kind of the different avenues or reasons why we would want to use either one of these algorithms.
Why wouldn't SARSA eventually over time, because it has some exploration, why would it eventually shorten its path?
Because the exploration is built into it. And because of this, you have to think of this in terms of exponential. Let's say there's a 95% chance that you do the optimal thing. I'm going to leave this as there are only two options. You can follow the cliff or you can fall off the cliff, just for simplicity's sake. So when you start here, there's a 95% chance that Q learning goes here and a 5% chance that it goes here. Given it's here, there's a 95% chance that it goes here and a 5% chance that it goes here. What is needed in order for it to go to the goal? A 95% success rate to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 consecutive moves. What is 0.95 to the 13th power? Someone with a calculator tell me.
One nine five to what?
0.95 to the 13th.
What's 8.51?
0.51. So there's about a 50% chance that Q learning falls off the cliff. And a 50% chance that it makes it there. With just a 5% chance of taking an exploratory action. We move the exploratory action from 5% to 10%. What's 0.9 to the 13th?
125.
0.25. This makes sense. Half the base, same number of iterations, it's going to be half as likely. So now there's only a 1 in 4 chance it reaches the goal, and a 3 in 4 chance that at some point along this path it falls off the cliff. So the exploratory actions compound when the exploratory action is a terrible thing every time, basically. So this is an extreme environment for this, but it really shows the difference between the two algorithms approaches. SARSA will never learn better than this because exploration is baked into the policy. There's no way to separate the exploration from the policy. And Q learning, while it is learning, is doing exactly the same thing. It will perform like SARSA. It'll act as stupid as SARSA was while it was doing this. It's going to look like it's stupid while it's training. And then from all of its mistakes, it learns the optimal path. And this kind of says something about real life as well. If you can be right at the point of failure, you learn the distinctions between failure and not failure very well, so that when you can analyze this and later decide, okay, I'm going to stop doing things to learn and I'm going to start doing things to perform, then you know exactly how to navigate this boundary. If you've always been held from taking risks or from trying things that are new, you're always taking that safer path, there's a limit to how effective you can be. You're always going to be somewhat effective, but you will never be cutting edge effective because you haven't experienced that boundary between success and failure. Yeah.
This is always the case with policy and on policy.
Yeah.
Like, even if it's like not the clip, but there's just one particular state that'll just say still be remote.
Yeah. Yeah.
Always gonna be like this.
Yeah. So SARS is mostly used in robotics, and the reason is if this cliff destroys your expensive robot, then you want to learn the robot, you want it to learn to path successfully and correctly, but you don't want it to take actions that are going to break it because it is expensive. So it's going to learn like this because we can't keep replacing the robot and replacing the robot and replacing the robot. If we got some grant for a lot of money and we have 100 robots to throw off cliffs, then we could learn with Q learning for the first 99 of them, and then our last robot would walk right along the cliff and have learned that path. So it is now learned for production. We could now go get even more money that shows we have a cutting edge robot that performs at the absolute best. And how many robots were sacrificed for that one robot to perform that well? The rest of them. The rest of them meant their end for the greater good. Although from the robot's perspective, they probably don't think it's the greater good. Be wary of the robots uprising. So yeah, SARSA and inexpensive times and places where failure is especially bad or expensive, Q learning otherwise, basically, is what boils down to why you would choose to use one algorithm over the other. And we see that when we go compare them as they are learning, that SARSA does perform better than Q learning. The sum of rewards here is higher than the sum of rewards for Q learning, but this is just while they are learning. SARSA reaches the goal more frequently and gets a higher score than Q learning does. And we find that it's especially volatile here with Q learning because where exactly it falls off the cliff and whether it falls off the cliff, we can get very lucky or unlucky streaks there. Like flipping a coin, you can get heads 7 times in a row and it's not that exciting. It's not that rare. It's rare, but not that rare. If you get 7 consecutive walking along the edge of the cliff and reaching the goal, then of course, it's going to look like the error is significantly less over time. And you get 7 in a row where it does fall off the cliff, and it's going to make it look a lot worse very quickly. So Q learning also has kind of small sample deviations in what that looks like as it converges, or it doesn't really converge because of that. Whereas SARS is much better at converging because it's more likely to get to the goal more frequently. One improvement we can make to SARSA to make it a little bit better is rather than using the maximum, like we did in Q learning, the maximum possible action, we use the expected value of that action, that state action pair. And if we use the expected value based on that instead of the maximum and then plug it into SARSA rather than Q learning. So SARSA took an action, and now instead of that action, we're going to use the expected value of the policy that SARSA has. So we know that we took an exploratory action, but that exploratory action, we were only going to take 10% of the time. So we update based on the expected value, regardless of the actual action that we took. So it is closer to Q learning than it is to SARSA, even though we say expected SARSA at this point. It's closer to Q learning than it is to SARSA, but it's basically Q learning replacing the maximum here with an expected value of what we're going to do at that state based on the policy. So far, we've seen 2 algorithms that involve some kind of maximization. SARSA uses epsilon greedy. Q learning has the target policy that it's trying to learn via some maximization. And if we end up with bias, how do we deal with that bias that we might find? Here's an example of this. So if we look at what happens from state A in this weird game, the immediate reward of moving left or right is always 0 from A. But if we take 10 actions in B, then we see that giving a reward from, it's a random number from -0.1 to 1. No, it's weight 1. We see that the best thing here is always to choose right, but we wouldn't necessarily be able to see that. So if when we see that, we move over to B and we get one single positive value. It takes a long time, and in fact, it will never reach 0 because it's always going to be, the value for that is going to stay positive. What do I mean by this? Because we start using the learning rate after the first example. So if we get that first positive example, we will kind of asymptotically approach 0, but we won't necessarily get there, even though the expected value is less than that. So we get what's called maximization bias. And if we use the expected value here, instead of the typical each time we see this, it's going to give us, we're going to update based on that value, then we end up not running into this problem. Probably not a ton here that we need to cover. This is getting a little bit beyond what I typically care about with regards to SARSA and Q learning, and you don't usually need too much of this in order to implement it. So I'm probably going to call this good for the RL section of the course. This is mainly what I've wanted to cover is through SARSA and Q learning. And for the graduate students, all one of you who are online, and anyone else who wants to do this, very frequently SARSA or Q learning is what you end up wanting to implement for a learner. Usually it's something like Q learning because anything digital, there's not much of a cost to that exploration to failure while you are training. You just want to make sure that there is enough training because eventually you switch from training to performing. SARSA is always learning because it's every single example it's able to continue to update. its learning and its performance are the same algorithm. Whereas Q learning has a learning behavior and a performance behavior. So this means that it's very challenging to use something like Q learning to adapt to player behavior because it's not learning. It has to train on the side. So you could go through some data collection, collect data from the player, then retrain, then end up with the new AI at the other end of that that's going to engage with the player. But depending on how long that training takes, that training can take, depending on how complex it is, minutes or hours or days. And no one has time to wait for an agent to retrain itself in the middle of a match or in the middle of a game. So you can use something like Sarsa as a workaround that's going to learn. And because Sarsa is not as bleeding edge efficient as Q learning, because it makes those exploratory actions, your AI will be making mistakes. Will be opening up holes for exploitation in a way that it's usually acting very intelligent, but occasionally it doesn't act very intelligent, and that is your opportunity to strike. Think of it like I can use Dogcha as an example from our last game when the human is very closely targeting the dog and is very close to it, but then occasionally the human turns around and walks away for a step or two. That is the opportunity for you to escape and go hide around a corner or go do something. That is the opportunity that creates the gameplay where even if you find yourself in a corner, there's an opportunity to escape. Something like that can be built in with Sarsa, where the exploratory actions, as it's gathering that data, as it's learning from what it thinks is suboptimal, that's when the player can create an opportunity. So that's another reason why you might choose to use Sarsa.
Wait, what did you say?
If you're using Sarsa, so you're training as you go, but Sarsa is going to be making exploratory actions as it learns. Those exploratory actions are an opportunity for the player to perform at that point. That's the hole in the AI that the player can exploit. That makes it seem fun to defeat and makes it defeatable. If you look back at how Sarsa is performing at the cliff walking example, when it decides to not be near the cliff because of its actions, it's trying to say that when I do make those exploratory actions, I don't want it to be terribly detrimental. That's what it learns. So it kind of places a cap on how good your AI is going to be because it's going to be planning for, like imagine an AI on a patrol route. If it knows every once in a while, I just go haywire and decide to turn in the opposite direction from the place that I'm patrolling, and then I turn back. If it knows that it does that, it's going to plan for doing that and try to optimize around the fact that occasionally I just do something that makes no sense. But that creates the opportunity for the player to sneak around behind them when they do that. That creates the opportunity for the player to do that. And it's built directly into Sarsa that it's suboptimal. And it's suboptimal because it makes exploratory actions. And it makes those exploratory actions to prove or to know the order of how good each of those actions are. On the other hand, if you use Q learning, you have to retrain. So either you're going to have trained before the player starts, or you're going to be incorporating the updates that Q learning makes at some point when there's downtime in the game. So when the player is going through a dialogue, the agent behind the scenes, retraining. And then it can take into account what it learned from the last section of player behavior if it can finish training within the time period of a cutscene or the time period of dialogue. Something like that. But because it is offline in nature, that makes it especially challenging to incorporate that new data on the fly. So it's in learning mode whenever it's interacting with the player, and then it needs to incorporate that learning into its performance at some point. Questions on any of this? So yeah, undergrads can get significant extra credit if you incorporate some kind of learning like this into your game. I intend to make this something like possibly 10% of your class grade. Because it is challenging, especially to do well. And in some kind of believable fashion, but for those of you who think you can pull it off. And have a game design where this naturally fits into some kind of agent's learning, I think it's a really good experience to work with. To have an aspect of your game that's actively online learning from what the player does. And if you'd like some further assistance on how to think about your game, this is something we can talk about on Friday, or we can make a meeting during my office hours to talk about incorporating it. What are the states? What are the actions? What are the updates? How do we, where in the scripts does this update go so that the action selection is intelligent? We can have all of those discussions. Anything else anyone can think of to ask? All right, since I don't really have much of a plan for tomorrow past what was going to be something like this, I think we can plan for a bit of a planning day. I want to talk to each group really before Friday even about what your plan is. So I'll just plan to walk around to each group and just get a sense of what are you doing, thoughts on incorporating this. So maybe tomorrow can be part of that time to work on incorporating this into games if you would like to. So we'll plan to do that.
But yeah,